want to thank everybody for taking the time to join today. Also want to thank our presenter, Dr. Lianjie Huang from Los Alamos National Lab. He's a senior scientist, a geophysicist by training and practice, and he will be talking today about the newest of the NRAP set of NRAP tools. This is a beta tool. It's now available on the Energy Data Exchange. The subject, as you all can see, is on the optimal design of microseismic monitoring networks. And I will leave it at that and thank our speaker, and I'm going to begin. Thanks.
Okay, thank you, Bob. So today I'm going to describe the NRAP tool we developed in recent years. So this is for optimal design of the microseismic monitoring network. And the work basically was done by a few people here in Los Alamos, Yu Chen, formerly Los Alamos, and now in Solomoye, Ken Chen and Kai Gao, still in Los Alamos, and myself. So the objective of this tool basically try to provide a tool for optimal design of the microseismic monitoring network using either service and or BohoJava for cost-effective microseismic monitoring at your geological carbon storage site. Basically, we try to provide a tool and then quickly run on the desktop, and then can give you an idea, what the geological need for monitoring a geological storage site. So here is the content of my presentation. I'm going to briefly describe the method and then go through the GUI of the NRAP tool. I'm going to show one simple application at the end to the functional CO2 EOR field. That's a part of the Southwest Regional Partnership Project. So the method basically, what we do is we develop a tool basically to determine the relationship between the hypocenter uncertainty of a microseismic event. I show like here on the right, like for example in the reservoir area, and maybe in the floodplain, whatever. And within the target monitoring region, this is the target monitoring region you define. And basically try to understand what's the relationship between the hypocenter uncertainty of all those microseismic events and the geophone distribution. So here, basically, we show maybe we can have a service geophone or BohoJava, and try to understand, how many of them we need, how to distribute, and then to determine what's the optimal cost-effective microseismic network. So here is a little bit more detail. So what we do is we develop a Acknowledgement to calculate P and S arrival time. So advantage using Acknowledgement is can handle the complex model better than the shooting or conventional ray tracing approach. And then we develop a simulated heat annealing approach, to search for the best hypocenter through minimizing the arrival time misfit between the data and synthetic. So here basically show a flowchart of the approach. So the idea basically is input a model, and then giving a seismic and receiver distribution, and then generate a synthetic arrival time for the entire model, and define target monitoring regions, and in this model, and then can generate synthetic arrival time for microseismic event in the target monitoring region. So invert for hypocenter using simulated heat annealing approach, and compute the standard deviation error of the invert hypocenter. And then we basically repeat for all possible distribution, and finally can find a turning point on this relationship, to determine how many receiver need for the microseismic monitoring. So the GUI of this tool is designed by Metric, or the company is Mid-Atlantic Technology Research Innovation Center, and using Los Alamos executable file. So the tool basically now can run on different platforms, including Linux, Windows, and Mac OS. And this GUI is based on Java. So to run this GUI, basically go to the directory and then just a file using this command. And then the first when you start this command, and then you can see the first window. This is a legal statement, and then you can see this window. And then you click on the OK button in the bottom, and you go to the next screen. So here, after you click OK the button, and then we will show this screen. And here there is several buttons here, enter parameter, and then has a file button, have a view of information here. So in here, basically now there is including acknowledgement, reference, and user menus. So this is the standard acknowledgement statement. If you click on acknowledgement, and then this is a reference. The first one need to update. It's been published. And then the last one, if you click there, you are linked to the menu. This is a PDF file, so you can open the menu. So that can give you more information in detail. So those are these three buttons. And then you click the button on the top left on the file. You can see basically enlarge here. You can see a few options here. Can plot the result, save the parameter basically for the simulation, run the simulation, and then also you can force to exit the application. So the next step basically is you need to enter the parameters here for the tool to run, and just click this button here. So after you click this button, and then you show up this GUI interface. So include a few buttons. So first one is a velocity model, and then also define the distribution area of a Javelin, and then define the target monitoring region. So also you can give the number of CPU core to be used to run the tool, and you can change because default here set to 1. For example, your desktop or laptop, you have 8 or 16 or 32. If you want to use half of that or 2/3 of that, you can change. You just enter the number here, and then that can reduce the time to run the tool. So also in here, if you want, after you enter everything here, you see, oh, I want to start over, and then you can return to the main page to click this button to start over. After you save all of the parameters, and then you can save and run. So click this button, save the parameter first, and then run the simulation. So now I'm going to go through how you provide a parameter. The first one is a velocity model. You need to provide a velocity model. And then one thing, because normally desktop or laptop, pretty small computer, so you don't want to run a very large model. So thumb of rule is the model size should be fewer than about 1 million grid points. If it's too large, it takes too long, and then maybe sometimes memory is not enough. So the thumb of rule basically is just less than 1 million grid points. So here basically is a warning here. So when you click here, this button, there is a multiple option to provide a velocity model. So the first one basically is just 1D value. You enter the 1D value here. And so for example, if you click here, there is a multiple option. One is manual input a 1D value. And then another two options basically is provide a velocity model and read from a file. So first option, I'm going to show you how you do the manual input of a 1D model. So you choose the first option, and then you change the number here, how many layers you want to use. Because we have default here is 1 layer, so that's homogeneous basically. And then you click apply. For example, if I choose 3, here is an example, and I enter 3. So we have a 3 layer. and then you need to define the thickness of layer. You keep the parameter here, all these parameters, for example, number of grip point, which direction, and then number of grip point and depth, and then grid interval, etc. And then you give each layer, what's the thickness. So make sure they are consistent with the parameter defined here. And then you can change the velocity value here for compression way and shear way. And after you define these, and then there is other two options basically to provide a velocity model. One is the read the 1D velocity model file in this option here in the middle, and then one is a 3D velocity model file. If you already create a file, you can just read from the file. So this is a previous model. This model I'm going to run basically both of them and later and show you the result. This is kind of a homogeneous model, and it's a 3-layer model. And then as I said, you can read the 1D model. And this is a 1D model file. You can read, for example, if you have a log file, you can read the log file here, or other you already prepare the 1D velocity model file. So in terms of the format of the file, let's describe in the manual, and basically it's a line by line. So you can check the manual, what's the format of the file, and after you prepare a file, you can just open the file here, and then the tool can read the model from a file. So another approach is a 3D velocity model. If you have a more complicated 3D velocity model instead of 1D velocity model, and then you also can read the lab velocity file by clicking here, and then you can read the lab file. So those are the basics, how to enter the velocity model. There's 3 different approach. One is a manual input, and then that can provide a layer, how many layers, and then another 2 approach, basically read from the file already prepared. So now the next step, you need to click this button and then to define the Javelin distribution area. So the Javelin distribution area basically is 3 options. One is a service Javelin, one is a BohoJava, another one is manual, basically also read from a file. So that can be, for example, combination of Boho or Javelin or whatever, multiple Boho, whatever, you can just define it. So simple approach, for example, the service Javelin, you can define that like this way. You can keep the model region, because you have velocity model, and then you can tell from where to where, that's the region here. Basically, you define the region. For example, here is a westbound. Basically, all this is a meter for the service network region within the velocity model. And this is the eastbound, for example, this is southbound and this is northbound. And this is define the region of that Javelin region, for the service Javelin. And that basic Javelin we distribute in that area. And then during the simulation, we will vary the number of Javelin within that area. So this is manually input. So manual input, basically, you can read a file from a file, and as I mentioned earlier, and then you can define the Javelin in different areas, different regions, and multiple, for example, multiple Boho, or combine the Boho in the surface or whatever. And another one is the BohoJava. If you're only using BohoJava, so you can define, for example, the top depth of a BohoJava array in meter and the bottom depth, and then all these other parameters. You can choose this option to define the BohoJava, and then you can define what's the region. So the last option you need to define is a monitoring region. So where to monitor? Because it depends on if you want to monitor in a reservoir or monitor in a fall. So you can define that region, and then for simulation. So here, for example, basically define, it's kind of square region, west, east, south, north, and top and bottom, for example, as a cube. You can define the region you want to monitor. And that basically within that region, we want to calculate what's the distribution of microseismicity, and then what's the hypocenter uncertainty versus the Javelin number of Javelin defined earlier. And after you define all these parameters, And the next step, you need to click this button, Save. So that basically save all of the parameter. After you save parameter, you click Run, and you will run the simulation. So in terms of how much time it takes to run the simulation, it depends on the CPU speed and the number of the CPU core you defined earlier to run the tool. So here is the example, when you click Run, and then we pop up progress bar here like this one, and then we show the job progress, step by step until you finish. And this is basically monitoring if the job is running or is stopped. If it's stopped somewhere, something wrong, something parameter wrong, you may want to stop it and exit the application. And then that is under here's a file, that is the option, basically exit application. So after you finish your run, result will automatically plot after the job is complete. But even now, you can click this button basically to plot the result, and then we'll show about the result. So I'm going to show you a few results, basically, just using the default parameter. And this is basically if it didn't change anything, and then you just run the model, basically, and then you show basically this is a default homogeneous model. And then you show this relationship between the standard deviation error of the event location versus the number of the geophone. And it's a service geophone, basically. And you can see that, with the increase in the number of geophone, the standard deviation error decrease. So if you can tolerate whatever value, you can choose that one, that's for example, this one maybe is 36 geophone, that's good enough for your monitoring. You don't need to use ISO 45, for example, it doesn't improve that much. And this is the result of the 3-layer model I defined earlier, as I showed earlier. So in this case, you can see that for the 3-layer model I defined, and then only 8 geophone need for cost-effective microsize modeling, as shown here. Because if you increase the number of geophone, the standard deviation error of event location doesn't improve that much. So this turning point basically gives you the optimal number of geophone need for cost-effective microseismic monitoring. So that's why I'm going to show you how we use this tool, to run one of the real applications. Basically, we use the 3D velocity model from Farnsworth CO2 ERR field. That's a part of the Southwest Regional Partnership Project or carbon sequestration, and Farnsworth in Texas. So basically, we define the model and define the surface monitoring area from what area to area, for example, we want to monitor. And then we run using this tool to run the simulation. So we find out this is the standard deviation or event location error, and versus the number of the surface seismic station. So you can see that in this example, using 16 surface geophones should be enough for cost-effective monitoring. So that's one of our applications to the Farnsworth Southwest Regional Partnership Project. And these kinds of tool, can be used on any side. Basically, if you can define the velocity model, either 1D or 3D, either you provide by a file or manually input a 1D model, for example, and then can run the tool, can give you the idea of how many geophones you need and then how you distribute. Because this number of geophones relate also the distribution of the geophone, because we define the area already. So that's the tool basically, we develop. So in summary, so we have developed this indoor tool for optimal design of the microseismic monitoring network for cost-effective microseismic monitoring at geologic carbon storage sites. And then the tool will be released soon pending of the NETL London approval. Currently, basically, it's been taking quite a while, basically, of a legal approval for open source release. And then that hopefully we can get it done, and then we can release the tool to public. So acknowledgement, this work was completed as part of the NRAP project, and then the support is from DOE, NETL, and we would like to acknowledge the several program manager and DOE and ETLO for their support. And we acknowledge the technical guidance from the NRAP Executive Committee. We would like to thank several people, including Erica, Corinne, Bill, and Alex, from different organizations for their comment and feedback of the beta tool. They carefully test the tool and then give us feedback on different platforms. And we thank Bob and Roger of Los Alamos for their support and coordination with the metrics, for the GUI design. And also, the last but not least, we thank Xiaoping Chu of Los Alamos for compiling the code on Windows OS. And we don't have a Windows compiler, on our computer, and then she kindly helped us compile the Windows, the code on the Windows OS. And that's all I have. I can answer any question if you have.
Thank you.
Sorry, go ahead.
Sorry, Leandre, this is George. Can I ask a question? So on this tool, this is a good tool actually. Does it take into account the elevations of the geophone surface thermometers?
Sorry, there's a popping sound. Can you repeat your question?
I said, does it take into account the elevation of the receivers of the thermometers surface?
Oh yeah, you can. Right. That's basically, you can define any location of the receiver. Basically, if it's you can define in a file, any position. There's no limitation. For example, like a BohoJava, I change in service, it can have a topography and can change. It can define in a file. And yeah, that's why.
Okay. Yeah. So it takes into account also the elevation on this. Also, if you remember, Leandre, when you guys designed this for us in Farnsworth, we went in there and because here you assume that you can put geophones everywhere or thermometers everywhere. We went to the field, of course, we have to move some around. Is there a way in the tool we can enter a shapefile or KMZ file with the infrastructure in the area to kind of limit the software limit where we put the geophones based on the infrastructure?
But the code cannot automatically, but you should basically, when you define a geophone the area, basically you can avoid that. And then what we do, basically, remember, we basically, after you adjust, and then we can recalculate what's the standard deviation, and then to see, normally it doesn't change much. And also in the more complicated case, we also it's not in the regular grid. We also have those kinds of can allow have a kinds of Gaussian distribution, of uncertainty of the geophone location, and then to calculate the standard deviation of the event location versus the number of geophone. And normally they don't change that much. It's pretty close. And that's why the design normally is like an ideal case. In practice, as you said, there is some variation. And for example, in the Farnsworth, eventually basically it's not a regular distribution, it's kind of irregular because as you said, there is some facility, we cannot put a layer, geophone layer, and then you can vary that, and then you can recalculate based on that, and then to understand what's the standard deviation you expect.
All right, so you can repeat it. You just figure out what your infrastructure, and you move your station based on the field conditions. Then you do the simulation again.
Yeah, do the simulation again. Basically, it's based on the new. Yeah.
Okay.
But we found out they don't change that. Basically, normally they don't change. It's pretty similar. Yeah.
Yeah, and in the case of the Farnsworth, I don't mean to belabor this, but in the case of Farnsworth, a couple of geophones, thermometers, we had to move them like a mile away. I can't say a mile away, maybe a quarter mile because of the infrastructure. But anyhow, yeah, thank you.
Thank you.
We got a quick question with regards in handling faults or existing, I guess, anisotropy within your layered model.
You mean the anisotropy in the fault?
When you define those layers for your geological model, do you have an option where you actually can define faults or some anisotropy within your I guess, synthetic model?
The current version of the tool, we only use isotropy case,
Right.
and then we do have a code, can run anatropy case, just take a longer time.
Mm-hmm.
And in principle, yes, we can upgrade the version, using anatropy ray tracing, and then do the same thing, basically, do the design.
Right.
Yeah.
Another quick question with regards to the previous question, I guess, is do you need to have a regular grid for your geophones, or you can just have any geometry? You probably mentioned that.
Yeah. You can define the image geometry, right? That's why I said that there's a menu input option.
Right.
Yeah.
Thank you.
Mm-hmm. Any other question? Maybe
so,
not.
Dr. Huang.
Go ahead.
Yeah, I'm Abhash Kumar from NETL. I was just wondering, so this tool can ultimately provide you the coordinates, possible coordinates of the geophone location that should be used to optimize the location of microseismic event?
So geophone basically is defined. Yeah, that's right. That's why, basically you define the region, and then we talk about number of how many geophone. Basically, is kind of regularly distributed there. Okay. That's how we calculate. But if it's manually distributed, you go back to which one corresponding to the turning point. So it depends how you input the geophone. Yeah.
Okay. Thank you.
Okay. Mm-hmm.
There are a couple questions in the chat window that I think are also related to geophone. I can read those.
Let's see. Let me see how can go to find a chat. Maybe it's
okay. Would you like me to read it?
It's locate on the surface. Location uncertainty same in depth in SYZ. The uncertainty is not the same as the depth in SY direction. They are different. We normally, here what we show here is the absolute distance. But in our code, in fact, we use that for geothermal, so we oftentimes show, on all direction. And that's one question. Another question, what's another question for the curve? We show. Yeah, that's why I said that, the geophone, it is defined. The surface area, like what I show you here, that will be regularly distributed, but you can define manually, and then you can, in your file, and then recalculate that. Is the only surface I'm looking? Yeah, as I said in the option, basically we have multiple options. We have a downhole BoHo geophone. One option you can input a BoHo geophone, and the option is a surface geophone, and the option is a menu. You can define it in your any location. As I mentioned in the tool. So I think that's all the question in the chat. Okay.
Okay. Are there other questions? So I will mention that if other questions come up after the call is done, you can either contact Dr. Hung, or you can email. Or you can always email the NRAP address, which is nrap@netl.doe.gov, and we will get a response back to you. So I'll see if there are any additional questions.
Maybe a comment. If the speaker can maybe comment on the magnitude of the events. Do you actually apply any type of threshold or for those events that you?
No. These only for the design of the, how you can detect a microseismic event. We don't. That's a different different modeling.
Modeling.
We did that for one of geothermal project, basically what kinds of magnitude you can expect. Thermal also can do that also. Yeah, but that's different. Yeah.
Yep. Thank you.
Okay.
Okay.
Yes. If there are no additional questions,
come back to you.
Yeah. I was just going to say, if there are no additional questions right now, then just want to thank everybody for joining and thank you for presenting. And we will be happy to answer any follow-up questions. Thanks for your time.